Section 3.5, Combustion Analysis. This is a section that will show us how we can use a particular experiment, an experimental apparatus, to determine chemical information. So the idea here under combustion analysis is that what we want to do is we want to determine the chemical formula of an unknown compound. This is very specific, though. We're going to look at a type of compound which is called a hydrocarbon. And a hydrocarbon must have hydrogen in it. It must have carbon in it. However, it might have oxygen as well. Or it might have nitrogen as well. Okay? But it definitely has to have hydrogen and carbon. So we're looking at very specific types of compounds. Now, as we saw in the previous section, if we take a compound such as this one right here, C6H6, this is called benzene. Benzene has a formula C6H6. So what that tells us is that there are 6 carbon atoms and 6 hydrogen atoms in the molecule. However, we have something called the empirical formula. The empirical formula is the smallest whole number ratio of the elements in the compound. So if we were to divide each of these numbers, each of these subscripts by 6, this would give us the lowest possible ratio of the elements carbon and hydrogen which comprise the benzene molecule. This is called the empirical formula. You just take the formula for the compound and divide it by the largest number that you can so that you still have whole numbers. Okay, so we could have divided it by 2, we could have divided it by 3, but the largest whole number we could have divided by was a 6. So if we do that, we get the empirical formula. This actual formula, C6H6, is often referred to as the molecular formula. So there are 2 different types of formulas here. There's the molecular formula, which is the actual formula of the compound. That's how many atoms of each element are in the compound. Then there's this empirical formula, which just gives us the lowest possible ratio of the atoms of each element that are in the compound. Now, you might ask, well, what use is the empirical formula? It turns out the empirical formula is sometimes used to determine the molecular formula. So in other words, if we have the empirical formula, there are ways to determine the molecular formula. So it's sort of a stepping point for figuring that out. It's an intermediate step. Okay? So up here in this figure is a diagram of a combustion analysis instrument. Most combustion analysis instruments are similar to this. What you do is you flow oxygen through an inlet port, which then mixes with the sample at high temperature. The high temperature takes place in a furnace, and what happens is high concentrations of oxygen gas with high temperatures will result in a reaction of hydrocarbons into carbon dioxide and water, and that's called combustion. So what will happen, let's say we don't know the chemical formula. So I'll write N and M to indicate that these are some numbers, but we don't know what they are. It will react with some number of oxygen molecules to form carbon dioxide, which is a gas, and water, which at the point of combustion is actually a vapor, so it's also a gas. Okay? That's called combustion. Now, here's the significance of that. If the sample is combusted in the furnace, we can run it through a catalyst, which is copper oxide, which converts all of the carbon that was in the sample into carbon dioxide and all of the hydrogen that was in the sample into water. Then we have what's called a water trap, an H2O trap, which in this particular diagram is magnesium perchlorate. And then we have a carbon dioxide trap, which in this particular example is sodium hydroxide, NaOH. What we do is you weigh the traps before the combustion, then weigh the traps after the combustion, and that difference in weight is the weight of the water and the weight of the carbon dioxide that was produced in the reaction. The hydrogen came from the sample, so if you can figure out how much hydrogen is in that water, that tells you how much hydrogen was in the original sample. Same thing with carbon. Carbon is sequestered in carbon dioxide, so once you weigh the carbon dioxide, you can figure out how much carbon was in that carbon dioxide, and that tells you how much carbon was in the original sample. And once you've got those masses, you can then determine the empirical formula. Okay, so here's the idea essentially. You have this trap which might just have magnesium perchlorate. So this is the water trap. Right? Let's say this thing weighs, 110.55 grams. Then the water vapor flows through. Some of it sticks. So the mass might go up to 111.25 grams. So the difference between those two, that'll give you the difference. That will be the mass of the water. Water has hydrogen in it, so that hydrogen had to come from the sample. So if you can figure out how much hydrogen was in the water, that tells you how much hydrogen was in the sample. Okay? So after that, it's really just an issue of calculation. So let me show you an example, okay, let me make some space here. There we go. Make some space here. So the example we're going to look at is for glucose. Oops. Glucose has carbon, hydrogen, and oxygen in it. I'm not going to give the numbers, but we'll figure that out by the end. So let's say we combust 18.8 grams of glucose. And when that happens, what we get out of it is 27.6 grams of carbon dioxide, and 11.3 grams of water. Okay? Let's find the empirical formula. For glucose. Okay, so here's how you go about it. The first step is to find the mass of carbon in the CO2, semicolon, hydrogen in water. So that's our first step. Once we've got those masses, then we can convert the mass of carbon to moles of carbon and mass of hydrogen to moles of hydrogen. Third step, divide the moles by smallest number of moles. And then step 4, round to whole numbers. And that gives us our empirical formula. Stepwise, 4 steps right there. There is one complication that can occur, but we won't consider that initially. Okay, so let's begin with our data. What we know is that glucose has carbon, hydrogen, oxygen. So our first step is we're going to find out how much carbon is in that glucose sample by figuring out how much carbon was in the carbon dioxide. So it's 27.6 grams of carbon dioxide, right? That's given. Then we look in the periodic table and we find that 1 mole of carbon, oops, sorry, skipped ahead a step there. We find that the mass of carbon in the periodic table is 12.01 grams per mole. That's the molar mass of carbon from the periodic table. The molar mass of carbon dioxide from the periodic table would be 44.01. Now, I'm not going to explicitly show you where I got that 44.01, but we learned that in the previous section, molar mass. Carbon dioxide has 1 carbon, and it has 2 oxygens. Carbon weighs 12.01, oxygen weighs 16.00. There are 2 oxygens, so that's 32.00. If you add them together, you get 44.01. So if you take the mass of CO2, then multiply it by the ratio of the molar mass of carbon relative to the molar mass of carbon dioxide, that will give you the mass of carbon that's in the compound. So let's bring up our calculator. 27.6 times 12.01 divided by 44.01. And you get 7.532. So that right there tells you the mass of carbon, not only in the carbon dioxide, but in glucose, right? Because the combustion reaction results in all of the carbon being converted from glucose into carbon dioxide. Now we do the same thing for hydrogen. So the mass of water is 11.3. We're going to multiply that by the molar mass of hydrogen and divide that by the molar mass of water. But be careful, because water, we know, has 2 hydrogens. So it's 2 times 1.01 grams per mole divided by 18.02. Again, I won't explicitly show you how to get that 18.02, but that's just the molar mass of water, 2 hydrogens and 1 oxygen. So 11.3 times 2 times 1.01 divided by 18.02, and you get 1.267. Okay. Now let's find the mass of oxygen. The way you find the mass of oxygen is you note that glucose has all 3 of these elements. If you subtract the mass of carbon and you subtract the mass of hydrogen, that'll just leave you with the oxygen. So for oxygen, we would take our 18.8 grams, that's the mass of the glucose, subtract from that the mass of the carbon, and subtract from that the mass of the hydrogen. So 18.8 minus 7.532 minus 1.267. And it's 10, almost exactly 10 grams, 10.001. That's your mass of oxygen, right? It's the total for glucose minus the mass of carbon and minus the mass of hydrogen. Now we have the masses of each. So the next step is to go ahead and convert these masses into moles. Interesting, right? So in the previous section, we learned how to do that. So it might be fresh in your mind, but you may not be really, confident in it yet. So let's remind ourselves how we do that. We have 7.532 grams of carbon. Converting to moles, we divide by the molar mass. Right? So 7.532 over the molar mass of carbon. .6271. Okay, that's carbon. Now we got to do the the hydrogen, 1.267 grams. Okay, now we're just doing hydrogen. We're not doing water, so it's 1 mole of hydrogen over 1.01 grams of hydrogen. Again, these numbers come from the periodic table. So 1.267 over 1.01, and you get 1.254. Last one, oxygen's 10 grams. So 10.001 grams of oxygen. 1 mole of oxygen is 16 grams. Okay. 10 over 16 is the same as 5 over 8, right? So 10.001 over 16.00, and you get 0.6251. Okay, so we've done what we would consider the second step. We found the mass of carbon, the mass of hydrogen, and the mass of oxygen. We've converted them to moles. I did it for oxygen as well because we have oxygen in this compound. Step 3, divide by the smallest. So I'm going to do 3 divisions, mole of carbon over the smallest. Of these 3 numbers, it looks like this one's the smallest. So moles of oxygen. So 0.6271 moles over 0.6251. Okay. So 0.6271 over 0.6251, and you get 1.003. Okay. Let's try now moles of hydrogen over moles of oxygen. The reason we're dividing it by moles of oxygen is that when you divide them by the smallest number, they should all work out to be whole numbers. So 1.254 over 1.261. Oops, is that right? 6251, right? Okay, let's try that again. 1.254 divided by, 1.254 divided by 0.6251. There we go. 2.007. And then the last one would be moles of oxygen over moles of oxygen. Well, that's 1, right? Okay, so now here's where you're at. You just essentially round them to whole numbers. We know that the empirical formula should have whole numbers. So we would round this to a 1. We would round this to a 2. And we would round this to a 1. And then the empirical formula, you just take these numbers and make them the subscripts. So C, remember with chemical formulas, if it's a 1, we don't write anything. H2, and then again it's a 1, so we don't write anything. And that would be our empirical formula. Now, sometimes there are problems where you may not be able to round directly. So here's what I would say. If the first number after the decimal point is a 0, just round it. If the first number after the decimal point is not a 0, so it's a 1 or a 2 or a 3 or 4 or 5 or 6 or 7, then you multiply through everything till they are whole numbers. So for example, if I had 1.33 and 2.66 and 1.33, see there the first digit, well actually this would be 1, I'm sorry. One of them's got to be a 1, 1.00. If the first digit in any of them is not a 0, then you're maybe not justified in rounding. So here's what you would do. You'd say, I'm going to multiply this by the smallest whole number so that when I do that, it becomes a whole number. So you have to know your fractions, right? A tenth times 10 is 1. A ninth times 9 is 1. An eighth times 8, so forth. 1.33 is really 1 1/3, so if you multiply it by 3, you get a whole number. Same thing here, if you multiply that by a 3, you get a whole number. And then you multiply that by a 3, of course, you'll still get a whole number. Okay? So that's if the first digit past the decimal point is not a whole number. But these are all zeros, so that's fine. So this would be the empirical formula. And we're done. Okay? So that's an important type of problem, finding the empirical formula from the mass data. Now, I want to show you one more aspect of these types of problems, which is that we generally aren't that concerned with the empirical formula. Generally what we want is the molecular formula, coming back all the way to the beginning. For example, if we have benzene, the molecular formula is what we want. We want to know what the actual number of atoms of the molecule is, not just the empirical formula. So here's what you do. In order to take the empirical formula, and so, for example, for glucose, it's CH2O. And for benzene, it was CH. We want to convert those to the molecular formula. Now, we don't know what it is for glucose yet, but we do know for benzene it was C6H6. So the difference between the empirical formula and the molecular formula was that we took the subscripts here, which are 1s, and we multiplied them by some number. What number did we have to multiply those subscripts by to get 6s for both of them? Right, we had to multiply by 6, right? So we're going to have to multiply this by some number to get the molecular formula as well. Now here, let me make a little more space here for us. A little more space for us. Here's how we do it. When you have the empirical formula, you need an additional piece of information. It must be provided. And that's the molar mass of the compound. The molar mass of the molecular formula. If you don't have that, you can't figure out the molecular formula. You need to have this molar mass. So for glucose, I'm just going to tell you. It's 180 grams per mole. Now that's a nice round number. It's actually 180.18 or 180.176, but 180 is a nice round number, and we'll just use that number there. Okay, that's usually all you need. So the idea then is you need to have this number. If you don't have it, you can't figure out the molecular formula. Here's how you use it. You ask yourself, how much does this weigh? And then you multiply the subscripts by a number that gives you that number right there. So for example, carbon is 12. See how I'm using a nice round number for this type of problem? I'm not using all the sig figs. The reason I'm doing that is this is a nice round number. Hydrogen is 1. Oxygen is 16. If you add all those up, you get 30 grams per mole. So then you just ask yourself, what do I have to multiply 30 by to get 180? Okay? I like to use the analogy of a train. If you were to say, look, this train has a certain number of cars, and one of them weighs 30, but you're then told that the whole thing weighs 180, right? How many cars do you have? What you would do is you just take the 180, divide it by the 30, and that would give you 6. See why that for this particular type of problem, it's nice round numbers? That means the molecular formula is 6 times as heavy as the empirical formula. And the empirical formula is just a ratio that should be the same ratio as the molecular formula. So we just have to multiply it by 6. So if we multiply this by 6, you get C6H12O6. And that's the answer. The molecular formula of glucose is C6H12O6, and you've got that by doing this ratio. So you take the given molar mass of the molecular formula, that's got to be given. You roughly estimate what the molar mass of the empirical formula is. Okay, so that's 30. 180 divided by 30 is 6. You multiply the subscripts by 6, and that gives you the molecular formula of the compound. And then you're set. You've got the answer right there. Okay, so this whole section is really just about how to do a particular type of problem, which is finding the empirical formula of a compound via combustion analysis, and then how to find the molecular formula based on knowing the empirical formula and knowing the molar mass of the compound. Okay?